So, okay, so today we're going to talk about the digital image and digital resolution. So we spoke so far in the first 2 weeks. We spoke a lot about bleed through and how we match our macroscope with the fluorophores in the sample. And we spoke a lot about the anatomy of the macroscope. I hope that you feel very comfortable now with how your macroscope works. And we're going to add a little bit with how we split the colors and things like this today or tomorrow, I can't remember. And then we spoke a lot about objectives because these are central for imaging and how we choose an objective. And also yesterday, or no, on Monday, we spoke about sample preparation quite a lot. And so today and tomorrow, we're going to talk about, yeah, digital images and how to capture light. So these two modules really hang together. There is a little bit of a, let's say, I'm going to add some information today about contrast, sampling, and optical resolution. And so I want to put things, let's say, the pieces of the puzzle together today. So bridging concept, optical resolution, contrast, and sampling. So what is a good microscopy image? A good microscopy image is rarely the most beautiful you can acquire. Okay, so I said before, your ugly images are your best friends. So you have a good microscopy image is an image that is good enough to have the image resolution. So what is image resolution? We're going to define this to reliably answer your scientific question. So your scientific question must be defined in terms of which metrics you're going to extract from the images, and then you work backwards with backwards design to try to figure out which objective do I need, which machine do I need, and which resolution do I need in my image. So the resolution in the image depends on several things. So what is the image resolution? This is an image that you're getting. What is the resolution? It is the smallest distance between 2 points in the sample. So this is in nanometers, that can reliably be separated in the image. This is what we mean by the image resolution. The image resolution is the final one that you're getting when you're analyzing. So that's the one that matters, really, is the image resolution. So the objective resolution is the resolution that the objective gives you. It doesn't mean it's the same thing as the one that you get in the image. Okay? So that's just the one that the objective is going to give you. So we know that the objective resolution is always worse in Z than in XY. So we get more information in XY than we get in Z. This is the nature of light that does this because we get diffraction and refraction, and therefore we always get a worse resolution in Z than in XY. But the image resolution depends on several things. It depends on the optical resolution that we have seen and we have spoken a lot about, 0.61 lambda divided by NA, and Z, 2n lambda divided by NA squared. It also depends on the aberrations in your sample. So even if the objective is giving you a certain resolution, if your sample is not prepared in such a way that you can extract reliable answers from your images, then this is what is going to limit the resolution in the image, right? And then, of course, it depends on contrast. So we'll speak a lot about contrast and the sampling. So let's talk about sampling. Now, the optical resolution is the one that we have seen before. This is the fact that the macroscope creates an image, an optical image of the sample, and the image of each fluorophore is an elongated blob with ring, like a rugby man, and this is called the point spread function. So I think you are very familiar now with the way the microscope treats the light that comes from our sample and what it does with it, and this is actually what we are recording with our microscope. So you remember that if we have two fluorophores close to each other, unfortunately, the 2 point spread functions, which are much bigger and very elongated than the original fluorophore in our sample, the 2 point spread function fuse, whereas the two fluorophores get closer to each other, and at some point we cannot resolve them anymore. And the limit of this resolution is the Rayleigh limit, which is the one that we are using, 0.61 lambda. Emission lambda, that's the one we have decided to use for this course, divided by numerical aperture, and this is for Z, and this corresponds to this dimension and this dimension. So the radii of the whole point spread function, which is actually double what we're seeing here. It's a big blob. And as I've said, there are other equations available, but this is what we are using here. So this is for the optical resolution. But now we also have aberrations in our sample, and the sample is part of the light path. And the issues that we could have with the objectives could be like the objective can be bad quality objective, and therefore, you know, the colors are ending up at different Z level, for example. The objective could be broken. It could be dirty. It's very common that people by mistake put oil on an air objective, for example, and that definitely needs to be cleaned. So that happens sometimes. But most of the time, the problem that we have is with the sample. When our scientific question cannot be reliably answered. Again, this is the goal, right? This is the goal of it, of everything, is that we get reliable answers. So if you can get reliable answer with what you're doing, fine, no problem. But if you need something a little bit finer, you have to be careful with the sample preparation. And in this case, we do not want to have scattering. We could have the wrong mounting medium. We could have a refractive index mismatch. And this is very common. All right. So now you know everything about all this, and you can ask yourself, is this preventing me from answering my scientific question in a reliable way or not? So in these cases, what we have, so either an objective issue or a sample issue, we have distortions, and the point spread function is elongated more than it should be, or it's a banana shaped or something like this, so it looks like a little star. And we have scattering of both the excitation and the emission as soon as we go away from the cover slip. So we have, again, a weird point spread function, and we can have dispersion, which makes the different colors end up at different Z planes. So this is, again, the image resolution depends on the optical resolution. It depends on the aberrations in the sample that are created by the sample, but it also depends on contrast and sampling. And this is what I'm going to talk about today. Yes. So let's talk about contrast. The contrast is often forgotten, unfortunately. This is the difference in intensity or color, so we can use color to contrast things as well, between the area of interest and its immediate surrounding. So you can see this very nice black bear that is walking towards us. And we could have a different, this image could be have a high resolution and a low contrast. You can see in here, we can see all the details of the hair on the fur. We can see the grass in here. So it's a high resolution image with a low contrast. And on the other side of the scale, we could have an image with a very low contrast. So we see zero detail, but low resolution, so no details, but we have a very high contrast. So you can see that what happens is that if we have a low contrast, even if we have a high resolution, we may not be able to work with the images. So there is a crosstalk between contrast and resolution. If an image has high contrast, but high resolution, I'm going to confuse you. I need to be careful. If an image has a high resolution, but no contrast at all, like this one, the resolution cannot be used. Even if we have done our best with the sample, this bear, put our sample on the cover slip, and we match everything, and we do our best, and we use a fantastic objective, we get an excellent optical resolution. We get no artifacts due to the sample, but if we have no contrast, it's not possible to use them. So it's the concept of usable optical resolution, right? The image resolution does not only depend on the optical resolution, it depends on other things as well. The problem with the microscope, unfortunately, is that when we image dense edges, so crowded things with lots of edges and dots, we will systematically have a lower contrast in the image. And this is physics, unfortunately. So the edges are sharp in the sample, but the imaging process makes them soft in the image. And when the sample is crowded, when there's crowded edges and dots, so you can see in here in each, so this is from David, one of his kidney images. And each of these lines has two edges, the beginning of the line and the end of the line, okay? So if we go across like this, we have 4 edges. So we have crowded edges here and we have a lower contrast. But if we have sparse edges, like in here, we have also the edge on one side and the edge on the other side of the dot, we have a high contrast because they're sparse. So when we look at the way it works in the microscope, we have, here we have an object, let's say, so physicists love lines like this. So they use these lines all the time to measure how the microscope functions. And so you can see these black and white lines like this regular pattern with the same width. This is our object that we put on the stage, and we're going to take an image of this so we can really control very well how the microscope is going to get an image of this. So when we look at the object and we measure the difference in intensity between the areas that are black to the area that are white, we have a certain height, a certain contrast. And this is 100% of contrast is going to be the difference between the black and the white intensity here. But when we image this, unfortunately, the image looks like this. And if you then draw a line across and you look at the contrast, you can see that the contrast has decreased. Okay, so the difference between, so this is a little bit gray and this is also a little bit gray. So we have light gray versus dark gray instead of white versus black. So we have a loss of contrast in the imaging, and it's always like this. But in this case, this is a quite well-preserved contrast. We go from 100% to 90%. If we use now an object where we have these lines are much thinner and we have a lot of them, so now we have a high frequency in the image. This is 100% contrast. This is what we have in the image. And when we look at the image, this is what happens. So we have lost a lot of contrast. And this is part of imaging, unfortunately. When in your sample, things are more crowded, small object crowded will lead to a lower contrast in the image. So when are high resolution and high contrast needed? If the sample contains crowded edges, then we must have a high resolution and a high contrast. And if fine details are important to answer our scientific question, we relate everything to the scientific question. If you do not need to be very, very stringent and be super careful to reliably answer your scientific questions, you're fine. You can do whatever and spit on your sample before you image it. You're going to get your answers, reliable answers. But if your scientific question requires you to differentiate between one thing and something that is quite similar, but a bit different, so small differences, then you need to be careful with everything. So define your scientific question and optimize the sample to get high contrast. So again, then in that case, if you need the high contrast, if you have things that are crowded, dots and lines are crowded and you must analyze them, you need to have a high contrast, so you need to have a very good sample, as we spoke about before. Oops. So you can see in here that something that is a high contrast is going to be much easier to segment, and something with a low contrast will be harder to segment, so harder to analyze. Okay, so how can we enhance the contrast then in a case? You know that when you use transmitted light, we can enhance the contrast with DIC, differential interference contrast, or phase contrast, for example. And these are two optical techniques to enhance the contrast in transmitted light images. But for fluorescence, which is like looking at the stars during the night, we can, if we want to use fluorescence instead of transmitted light, we know that fluorescence already has inherently, because of the black background, we have a better contrast in here. So it's to get a good contrast, it's better to use fluorescence than transmitted light. We can also get optical sectioning. So we can use single point or multi-point confocals. We can use light sheet or multiphotons, which has the capacity to do an optical sectioning, and this instead of wide field. So wide field is a low contrast method. If your scientific question does not require high contrast, you're totally fine with wide field. But if you need a high contrast, you're going to have to use an optical sectioning method. And of course, we then, if we need a high contrast, so if we have crowded edges and dots in our sample that we need to analyze, we need to prepare the sample with low scattering and refraction. So you know the whole thing. We need the sample to be as transparent as possible, so clearing it, and then match the refractive indices, everything on the cover slip and the correct cover slips. But there is more, and we will talk about this today. We can improve the signal to noise and the signal to background ratios. So in two ways, these are ratios. So either you increase one or you decrease the other one to improve the ratio. So you can increase the signal or you can decrease the noise or the background. And both of them have the same effect. And we will talk about this today. So you can see in here in this image of a grid, again, this is like the way to measure the performance of a lens, be it for microscopy or for photography. So you can see in here in this image of this grid, there is like a high noise in this image. But these lines are anyway image. So there is anyway a high resolution, but because of the noise, the resolution is hidden. And now if we work on things, let's say, to decrease the noise, and we will talk about it later, we can see that the objective does resolve these lines. We can see them now that the noise is reduced. We can see the very fine lines here. So we get we can use the optical resolution when we decrease the noise. Otherwise, the noise can hide and prevent us from using the optical resolution. So without contrast in the image, it's not possible to resolve details, even with excellent optical resolution. Improving the contrast increases the resolution that we can use, and therefore the image resolution. So that's what we're talking about today. So confocal pinholes are there to increase the contrast. So some systems have optical sectioning capacity, this we have seen. All systems except wide field. So only when we have an optical sectioning capacity, only the photons from a thin optical sections actually make it to the sensor and are imaged. So this increases the contrast because we're getting rid of the things that are out of focus. On light sheet and multiphoton microscopy, only the plane of interest is excited, whereas in confocal microscopy, so single point confocal or multi-point confocal, the spinning disk, the shape of the excitation is a double inverted cone, and that means that we are bleaching above and below. But once all these fluorophores are fluorescing, we throw away everything that comes from above and below, and we keep only what comes from here, and this is what we send to the center. Okay, so the planes above and below the plane of interest also fluoresce and are bleached, and they emit light. But the pinholes reject the light that comes from the autofocus plane, and therefore we're increasing the contrast. So this is what the pinhole is doing. It's increasing the contrast, except when you close the pinhole more than one area unit, then you're also increasing the resolution. Okay, but up to one area unit and above, what we're increasing when we close the pinhole down to one area unit is we're increasing the contrast. So I remind you that how the pinhole works is that, okay, here we have the image in X, Y, and in Z of our small fluorophore in our sample. And when we close the pinhole, we are actually making a mask in here. So we have a field stop that rejects all these things. So the size of the pinhole is going to be one area unit. And then it's magnified by the objective. So the physical size of the pinhole is the size of the resolution multiplied by 2 because this guy here is only the radius, right? So we multiply by 2 to get the whole disk, the whole diameter, and then multiply by the magnification. So this is the physical size of the pinhole when we close it to 1 area unit. So closing down the pinhole to 1 area unit improves the optical resolution, so the contrast, and also the usable Z resolution. So it improves the contrast in Z a lot, down to 1 area unit. But if you close it more than 1 area unit, it actually improves the resolution in XY. Okay, so that is very useful to close the pinhole. So closing the pinhole smaller than 1 area unit improves the XY resolution as well. In here you can see. And there is some sort of a sweet spot around 0.7 area unit, where if you close down more, you're only losing light because you're throwing away most of the light of the main blobs. So mostly 0.7 area unit is more or less where you stop gaining, at least in Z, but then you can continue gaining in XY, but you lose a lot of light. So you need to have extremely bright sample to close the pinhole under this type of, but you can. But at some point it plateaus. So then there's no point in closing even more because just losing light and not improving the XY resolution. So now we spoke about contrast and how important it is for us to use our the resolution that the objective is delivering. But now we're going to talk about sampling. So sampling or digitalization or pixel size, and I'm sorry, but some of my pixels, the word pixel, somehow I have managed to delete most of the word pixels in my lecture, the whole lecture. So I spent quite a lot of time trying to figure out where it is, and now this one is missing. It should be pixel size. So sampling, digitalization, and pixel size. Modern microscopes all acquire digital images. So we don't have analog images with a film camera anymore, because it's so much easier to analyze. I mean, it makes it possible for us to do a lot of things, but we have to let go with some things as well. The analog images had a better resolution than anything that the digital images can do. So a digital image is a matrix of picture elements. So I remind you that pixel means picture element, and each pixel has an XY coordinate and a uniform intensity value. So if we use small pixels, so this is our sample. If we image the sample with small pixels, and again, it should be pixels, this is what this is an image that we get. And if we image with large pixels, this is the image that we get. So you can understand that we have here the same objective, the same wavelength. So we have the same optical resolution. We have the same sample as well. So same optical resolution, same aberrations from the sample, but we get different pixel sizes, and therefore we get different digital resolution, okay? So the image resolution is affected as well. So you can see that the resolution that we get, the final resolution that we get in the image, does not only depend on the optical resolution, but also depends on the digital resolution. This is what we're talking about here. So the optical resolution is the distance between the details in the sample that can be resolved by the objective, okay? A high resolution is a small distance, so it depends on the spread of the PSF. If we have a big point spread function, that we will have a low resolution because they bump into each other quickly. And if we have a tiny point spread function, then we get a higher resolution. But in our sample, we don't have just one fluorophore, right? We have many fluorophores. And so let's say that this is the image of our sample that the objective forms. So this is the optical image, right? So it's a bit blurry because it's all distorted with the point spread function. To fully describe this image, this optical image, we would need an infinity of values because this has an infinity of contrast. But in the digital image, we can only measure intensities as integers and only on discrete XY points. And these discrete XY points where we measure the intensity are called sampling points. So it's very confusing. I'm sorry about this, but we have sample and sampling. The sample, and these are completely different. The sample is the object. So it's the specimen and the thing that we put on the stage. So it can be our tissue, our cells, and these are called samples. But we also have sampling, and this is an action. This sampling means taking discrete measurements of something that is continuous. So it's also called digitalization because we are putting digits, measurements, numbers, basically, on something that is continuous. So we go, here I'm measuring, here I'm measuring, here I'm measuring. Okay, so this is sampling. So now we have here in this optical image, we're going to take 3 measurements of intensity, one here, one here, one here. So we have 3 sample points. In a single point confocal, as you know, these sample points are acquired one by one. And in a camera-based system, bloom, all at the same time. So now we get the digital image where we have 3 measurements, one in this XY position, and here we have 2 colors. So either we acquire the 2 colors, the intensity together simultaneously or one by one. But anyway, we get 2 numbers, one for the red and one for the green. And then in this second sampling point, we have another value or 2 other values, and then more here. And so we have 3 XY positions, and we have a value for each color. So you can see that the digitalization process leads to a loss of information. Clearly, there's a lot more information in this image than in here. This is a rough simplification of what our sample looks like. So what are the real intensities, the intensity values between the sampling points then? Well, we will never know because we will never measure them. And the software extrapolate between the sampling points. So it's going to put like a border exactly in the middle of the 2 sampling points and say here, right? So the digital image is a rough simplification of the optical image, which itself does not look like the sample. Okay, that was also transformed by the point spread function. So it is not the same. This is the reason why at the beginning of this course, I said the image of the sample is never and cannot be like the sample. We have many layers of transformation between the sample and the final image. So the pixel size, I'm missing one word, pixel size in the image is the distance between sampling points in the sample. So this distance here is the pixel size. And again, I'm missing pixel, okay? And that would be in nanometers. So it corresponds to the distance of the sampling inside the sample. And if we have a higher density of sampling points, then we have smaller pixels, image pixels, and we have more accurate data. So if instead I would have half the size of the pixels, I would have more sampling points, and so I would have a smoother gradient here between the red and the green. Okay, so more accurate data with more pixels and smaller pixels. So how dense should the sampling points be then? So now this is when we're talking about Nyquist. So the Nyquist sampling theorem is also called Nyquist sampling criterion. It's the same thing. So hello, my name is Harry Nyquist. Well, actually, my name is really Harry Nyqvist because I was Swedish. And I came from Sweden with my parents to the United States when I was, I don't remember, something like 7 or something like this, and lived there. So he's American. And at that time, what they were doing is they were changing and Americanizing their name. So he became Harry Nyquist. And he was an engineer working with telegraphs and lots of other cool stuff. But he was trying to figure out, if I have an information like this that I want to send to you with my telegraph, so it's a periodic signal, how am I going to send you this information? What do I need for you to understand this information? How many sampling points do I need to measure along this line for you to be able to reliably reconstruct this signal? Do I take loads and loads and loads of sampling points? Yeah, it's fine. You will be able to reconstruct the signal reliably. But it takes a lot of time and it's a lot of data, right? So what is the minimum that we can take? What if I take only 2 per period? Because this is a periodic signal. What if I take only 2? Yeah, you should be able to reconstruct that way. Well, it depends, because if you're unlucky and all the points end up on a straight line like this, you will think that this is what the signal looks like, and that will clearly be not reliable. Okay, so what Nyquist said, the Nyquist sampling criterion is very simple. It's like we need more than 2 sampling points per period to sufficiently and fully describe the curve. Okay, so that is the Nyquist sampling criterion. Anything has to be sampled more than twice to be reconstructed properly. So why do we care? No, now we're talking about XY, okay? So the Nyquist sampling criterion in images, XY. So it also works for microscopes, not only for telegraphs. And it defines the sampling density needed to accurately digitalize the optical image formed by the objective. Okay, so this is exactly what we're after. How do we sample this optical image? So if we undersample, we will create aliasing artifacts in the image. So I will talk about aliasing artifact a little bit later. And the optical resolution, as we know, is the distance between 2 objectives that can be resolved by the objective. And that corresponds to the radius of the point spread function. So radius in XY, radius in Z. That is the optical resolution. So we have seen this many times. And the limit of what we can resolve in this course, we say 0.61 emission lambda divided by the numerical aperture of the objective. The Nyquist sampling theorem for line microscopy really should use 2.3. And I think I will change it for the next year. But in this course, we're going to use 2 just to make it easier, okay? So normally for digital images, the factor is actually 2.3 and not 2. But in this course, I'm going to say 2 all the time just to make it simple. So for the details resolved by the objective, so the optical resolution, to be accurately represented in the digital image, there must be more than 2 sampling points in this distance of the optical resolution. So the optical resolution is a distance, and it represents the radius of the point spread function. So within this distance, we need to have 2 sampling points. Otherwise, we will not be able to reconstruct the image in a correct way. Okay. So having 2 sampling points with this resolution distance, optical resolution distance, ensures that the image recording resolves digitally what the objective has resolved optically. So I often say something. Imagine that you buy a super duper X-ray. So nobody buys X-ray discs anymore, right? But you want to watch a movie and you buy a very, very good, very high quality X-ray movie. And you get the X-ray, and then you put it in in your reader, and you project it with a crappy projector. Now you understand that even though you have paid a lot of money to get a great quality movie, you are not going to see a great quality movie because your resolution is limited by the projector. It's exactly the same thing. On the microscope, the resolution in the image can be limited by different things. We can get a fantastic objective if we are not recording the image digitally in the correct way. We are not going to get the resolution that the objective has resolved. So the distance of the optical resolution must be sampled more than twice. So this is what Nyquist said, more than twice. 2 is not enough because otherwise we can get a straight line. If we want to accurately represent the point spread function. And again, we will see in which cases it's okay not to accurately represent the point spread function. It's always a question of choice, right, in microscopy. So for an image to fulfill the Nyquist theorem, this is what we say. If we want it to fulfill the Nyquist theorem, the image pixels must be smaller than this. So we must have more than 2. Okay, so we calculate how much is 2, and then we say, no, we could have them smaller than that. Then we have more, we have higher, we have more pixels in it. Small pixels means better digital resolution. So in a small image pixel, we get a better digital resolution. And now we're going to see how we calculate the optical resolution. So we know how to calculate the optical resolution, right? This is this one, fine. So the software always shows you somewhere where the pixel size are in the image. So I'm missing pixel here again. So you know how to calculate the optical resolution. You see in the software what the pixel size are. So it's quite easy. You can deduct if your images fulfill the Nyquist criterion or if they are undersampled. So here we go. We have our 2-point spread function are very close to each other and they are at the limit of resolution. So the distance between them is actually the radius of 1-point spread function. And now we want to sample this optical image by taking lots of sampling points. And so we reconstruct the image with all the information that we get from the sampling points. But we could reconstruct the image with smaller pixels or larger pixels. So if the image pixel size, the image pixels are smaller than half of the optical resolution, which is the case here, because we have here the optical resolution, and you see it sticks out a little bit. So these pixels are smaller than half of the radius. In that case, the sampling fulfills the Nyquist theorem. So this is the optimal if we're just a bit above. But if we have bigger pixels, so in here you see we have 3 pixels, so the size of 1 pixel is 1/3 of the optical resolution in this case, we are oversampling. So we have many tiny image pixels. We're oversampling, but this also fulfills the Nyquist theorem because we said at least. So there should be not at least more than 2, but this is also more than 2. So if we're optimal or we're oversampling, we anyway fulfill the Nyquist theorem, okay? Because it's more than half the optical resolution. So if we oversample, it does not improve the resolution beyond the optical resolution. So oversampling like this is not going to make our image better. It will take more time. But it's mostly not very useful to oversample, except when you want to deconvolve. So I said we use here a factor 2. It should be actually 2.3. But when you deconvolve, you want to have a factor 3, at least. Okay. So for deconvolution, this is useful. Otherwise, no. It just wastes your time. The resolution in Nyquist sampled images is limited by the objective. So in this case, we make sure that the digitalization is not what limits the image resolution, okay? So in a Nyquist sampled image, the image resolution is the same as the optical resolution. Sorry. If the objects in the sample are closer than the optical resolution distance, so they cannot be resolved because the objective cannot resolve them. If we undersample, so we get 2 big samples, 2 big pixels, then so we have fewer pixels. So on a single point confocal, it takes less time. The sampling does not fulfill the Nyquist theorem in this case. So the resolution in an undersampled image is limited by the digital resolution. Okay. And in this case, what is the since the image resolution is not the same thing as the optical resolution because we're undersampling, what is the image resolution? Well, it is the size of 2 pixels. So if we were sampling correctly, the image resolution would be just the size of the point spread function. But if we are undersampling, it actually becomes the size of 2 pixels. So you can imagine that as we get bigger and bigger pixels, we have a worse and worse resolution. Okay, so 2 objects that are closer than the digital resolution are not resolved. Okay, so what happens for a single point confocal then? What are the consequences? On a single point confocal, as we know, the fantastic stuff about single point confocal is the flexibility. We can adjust lots of different things. Like, for example, we can do spectral imaging and everything, but we can also adjust the image pixel size to match the requirement of any objective and any wavelength. So that's a great flexibility. So changing the image pixel size on a single point confocal, how do we do that? We have 2 ways, and they talk to each other. So we can change the scan area, which is the zoom, or we can change the number of sampling points. So it's the number of image pixels. So we can change the number of pixels, or we can change the zoom, and that results in changing the image pixel size. So for example, we're going to have a scan area of whatever 123 microns. So this is the area. This is the size of the image. So it is this the area in the sample that we're imaging is the scan area. And if you have a high zoom, you're going to image a smaller area than if you de-zoom. And then we have a number of sampling points. So we decide, okay, this is my zoom factor, and now I'm going to put 1024 pixels in that, okay? So this is 1024 by 1024 sampling spots. And the image pixel size is going to be basically the scan area divided by this. So we end up at 120 nanometers per pixel. So each pixel is 120 by 120 nanometers when we have this scan area and this number of pixels. So if we now use a higher zoom, we have a smaller scan area and we have a higher digital resolution because the pixels are smaller. So I have a better digital resolution, but we have a smaller field of view. So we always need to compromise. If we now decide to have less pixels, we're going to have larger pixels and therefore we'll have a lower digital resolution, but we have a faster scan because we don't need to jump between too many spots. In a single point confocal, there is a very convenient magic button in the software that gives you the optimal pixel size for the objective and the wavelength that you are using. And it is called, depending on the software, it can be called optimal or it can be called Nyquist. Okay, so I think in almost everywhere it's called optimal, but in Nikon it's called Nyquist. So now you know why. So the typical mistake of a beginner, microscopic beginner, who wants a higher resolution on a single point confocal is to change to a higher magnification objective without checking the numerical aperture. And you know that what matters is not the magnification, it's the numerical aperture. And therefore, they are reducing their field of view. I want more resolution, I want to use the 100x. That is so typical of a beginner. And at the same time, then they realize they go very, very slow. And so they want to, they undersample. So they use big pixels to go faster. And the result is that the image is limited by the digital resolution. So on a single point confocal, use the magic button, except if you have a reason not to. And we will talk again about what am I doing with this image? Do I need to have this resolution or not? It depends on if you can extract reliable answer from your scientific question. Now, what happens on I'm looking at the time to see how I'm doing. Okay, I'm not doing so good, but I should be okay. So when we look at Nyquist sampling for a camera-based system, what happens? On a camera-based system, we want to be fast, but we have very low flexibility. So cameras have pixel size of a fixed size because this is a device, the recording device of the camera. Unfortunately, camera pixels are different from image pixels. I remind you, the camera pixels are the physical recording devices on the camera chip, and they have a fixed size. It's just the size of each recording device. So they are large, and so they are in microns. And the image pixels is a completely different thing. It's a matrix of number that we use to build the image. So the numbers are X, Y, and intensity for each pixel. And their size depends on the sampling point in the sample. So they are small and they are in nanometers. So sorry about that, but we have to make do with this. So camera pixels vary greatly between 3.45 micron to 16 microns. And you can consider camera pixel as some sort of a bucket when it's raining. So if you have lots of buckets next to each other and it's raining, and the raindrops are actually the photons, the bigger the bucket, the more you'll get water in the bucket, okay? So when we have large buckets, large camera pixels, we get many photons, so they have a higher sensitivity. But a small camera pixels, we get a lower sensitivity, but higher sampling capacity. So we have a better readout, a better optical resolution with small camera pixels. So unfortunately, on a camera-based system, there's no magic button. But that's the way it is. So we have to calculate ourselves, but it's quite easy, really. We have the image pixel size, and then we have the camera pixel size, and it's divided by the magnification. So in that case, in digitalization, on a camera-based system, the magnification matters. That's the only time where for digital resolution on the camera-based system, the magnification matters. Otherwise, it doesn't matter. So if we have a 60x objective and a camera with 6.5 micron pixels, the image pixel size is going to be 6,500 because 6.5 micron in nanometers divided by 60. So 108 nanometers are the image pixel size. So it's quite simple to calculate it. So in here, for example, we're going to have 6 microns is a fixed size. And here in between, we have the magnification. So in here with the same objective, if we have a 60x objective, we're going to get 100 nanometers in this image. The pixels are 100 nanometers. So on the camera-based system, how can we change the pixel size then if we don't have a magic button? We can get bigger pixels by binning. So binning in a camera means that we are putting 2x2. If we choose a 2x2 binning, we can put 2x2 pixels, so 4 pixels together to make one. So 4 camera pixels to make one image pixel. I should be pixel here. So then this is called binning, and that means we have brighter images because we have now a big pixel, and we also have a lower resolution. So this image is acquired with no binning. Here is 2x2 binnings, and if we zoom in, we can see the pixels here because they are bigger, but you can see also that the image is brighter. So that can be great if you need to do an overview, for example. It's fantastic. You also get faster image processing. Why? Because it's easier for the software to process less pixels than having tons of pixels. In here, you will have 4 times more pixels. So bin the camera, for example, if you want to acquire an overview of a large sample with low illumination, so you don't bleach it, on the camera-based system, you should definitely bin the camera 4x4. Then you get an overview of your sample and it goes very quickly. Now, how can we get smaller image pixels then? Because the image pixels depend on the magnification, we cannot change anything to the camera pixels. Where we could, but then we would have to buy a new camera, and that's very expensive. We're talking about 25,000 euros, for example, for a camera. So very expensive. So we're not changing our camera in general. We're stuck to whatever we have on the camera. So and then also if we choose a camera with smaller pixels, we get dimmer images. So that's a little bit of an issue. But what we can do is increase the magnification. So clearly when we increase the magnification, we could change the objective, but we can also add extra magnification. So the objective, when you change the objective, it has lots of consequences. We know why we are choosing an objective versus another, but we could just add an extra magnification in there. And so at the end, when we have the image pixels, they are the camera pixels, so in nanometers, divided by the total magnification. So I said total magnification, I always mean the magnification objective of the objective multiplied by the extra magnification lens that we're adding there to make smaller pixels at the end. So here is an example. I think I'm almost finished. So yeah. Here is an example when we use a 40x objective with a numerical aperture of 1.25. So it's a silicon objective, and we have a camera with 6.5 micron pixels. The image pixels is going to be 6.5 microns divided by 40, the magnification. So it's going to be 163 nanometers. This is the pixel size in the image. But when we image a green fluorophore, so at 520 nanometers emission, with that objective, the optical resolution is 0.61 emission lambda divided by Na. We know this very well. And that is 254 nanometers. So we have a digital resolution at this magnification. And with this camera, we have a digital resolution of 123 nanometers. But our optical resolution is 254 nanometers. So you can see that the image pixels are larger than half of this. So half of this would be 127. Our image pixels are too big to digitally resolve the optical resolution. So the digital resolution in this case is limiting. So we're limited basically by the camera and not by the optical resolution of the objective. The sampling does not fulfill the Nyquist theorem. So we are undersampling in this case because the digital resolution is bigger than half of the optical resolution. So the image resolution is actually, instead of being this, it's double of the image pixel size. So it becomes 326. And if we were sampling correctly, our image resolution would be 254, the same as the optical resolution. Okay, but if on our microscope we have an extra magnification lens of which adds 1.5x, for example, which we have on the Nikon microscopes, then in that case, we are talking about the total resolution. So the image pixel size becomes 108 instead of 163. The optical resolution is the same. We're using the same wavelength and the same objective, so 254. In this case, the image pixels are smaller than half of the optical resolution, and therefore this image fulfills the Nyquist sampling theorem, and the digital resolution is not limited. So that means the image resolution is the same as the optical resolution, 254, okay? Because we have the same objective, the same lambda, and the same camera, but because we add this extra magnification lens, we get smaller image pixels and we can resolve our optical resolution. Okay, so now I have a little quiz for you. The most common 100x objectives are the same numerical aperture as the most common 60x objective. So the most common 100x and 60x objective have a numerical aperture of 1.4. So why would anyone ever want to use a 100x objective with an NA 1.4, considering that they both have the same X, Y, and Z resolution, optical resolution, and that the 100x is much dimmer and has a much smaller field of view? Can anyone tell me? Why would we want to use a 100x objective instead of a 60x objective?
If the person is using a camera-based system, then the digital resolution is the camera pixel divided by the magnification. And so with the 100x objective, this person can get a better camera pixel. And if this pixel is smaller than the optical pixel, well, when you use 60x, that digital pixel is larger than half of the optical resolution, then
Good.
the person may want to use the
Yes,
100x.
absolutely. Absolutely. So you said the camera pixels, I think you meant image pixels. We cannot change the camera pixels, right? They are where they are. We can't do anything. But by adding some extra magnification here, we are making, actually, even though we're adding magnification, we're making our image pixels smaller. Bit counterintuitive, but if you think about it, we have this grid of pixels on the camera, and we're magnifying the image more, and therefore we have more pixels. We have more sampling points inside this big image. So when we're adding magnification, we're actually making the image pixels smaller because of that. And that means that we can resolve. So this is absolutely true. If one image is on a camera-based system and the camera has large camera pixels, then you need to increase the magnification to fulfill the Nyquist theorem. And we will see why now after the break, why we need to increase the Nyquist theorem. So I'm sorry, I'm a little bit late. I think we're going to, anyway, just come back at